Okay. Can everyone hear me? Like to start with?
Yep, we can hear you.
Yes.
Okay. Okay. Sorry. I'm just Zoom is like the worst for the government computer. So, um, and then you're gonna like I'm gonna set up the slides, and then David will be talking, Scott will be talking, then I'll talk, and then we'll end with David. And if I'm just going to give everyone a warning, they're ripping up our back parking lot today, so there'll be some noises or vibrations going on. So, but I'll mute myself. I just want to make sure it shares here. I'm. Did I start sharing already? So you're seeing
No,
yourself?
Not yet.
No. Okay. Okay. So let me try because let's see. Let's try this. I'm hoping. Okay. You should see a blank screen.
Yes.
And we're going to go to this. And do you see that?
Beautiful. Yes,
Okay.
it's
Now I got
perfect.
to get myself back to mute myself here. Okay.
Gardner, I can mute you for you if you'd like.
If you, yeah, that would be great to start
Okay.
with. Yeah.
So yeah, I'll kick us off. Gardner, you can go ahead and go to the next slide. Thanks for controlling the slides for us. So in general, this presentation includes two parallel and associated items. The first item includes our first 3 bullet points here, which is the development and the approval of a policy and guidance document for establishing a hydraulic design criteria and an associated definition of the ability to meet the full stream crossing standards to the maximum extent practicable under Massachusetts state regulations. The second item of the presentation is the development of a statewide hydraulic model as a stream crossing planning tool to develop preliminary stream crossing designs. So yeah, I'll start the presentation by going over the problem statement and the beginning of our existing regulations. From there, Scott will provide an overview on the foundation of the stream crossing standards, the ability to meet the stream crossing standards to the maximum extent practicable, and the fundamentals behind our proposed policy and guidance. From there, we'll transition to the hydraulic model itself, providing an overview, and then Gardner will present on the technical details. So, and then questions to follow. So, yeah, next slide, Gardner. So our problem statement, in Massachusetts, we have over 25,000 small stream crossings. Many of these are undersized and in need of replacement. The obvious problem, though, is there a lack of funding to replace all these structures, and even more so, a lack of resources for departments of public works and towns to identify, plan, design, and prioritize replacement of all these undersized or failing culverts. So the problem and the potential remedies to this problem were studied by a Massachusetts Culverts and Small Bridge Working Group. The results were given to Senator Hines in the Massachusetts legislature within a document titled Improving the Efficiency of Culvert and Small Bridge Replacement Projects. And that document was released in September 2020. And so the development of the policy and guidance and the tool that we're talking about today all align with the findings and the recommendations that were provided in that report that were given to Senator Hines. So next slide. So we just have one slide here on our existing regulations. So this isn't intended to be a comprehensive overview of Massachusetts regs, but it's important for us to distinguish the requirements between new crossings and replacement crossings. And so for all new crossings in Massachusetts, the regulations require compliance with the Massachusetts stream crossing standards. And that those require designs that span the channel width at a ratio of 1.2, along with specifying an openness ratio and other criteria. So Scott has an additional slide on this in the slides to come. But this requirement for new crossings is essentially the gold standard. For replacement crossings, our regs require that design meet the stream crossing standards to the maximum extent practicable. In the regulations, there are 12 criteria that should be assessed before a maximum extent practicable finding can be made, and that those some of those criteria include potential for downstream flooding, upstream, downstream habitat impacts, and many more, along with the cost of the replacement. And so our goal with the proposed policy and guidance that we're talking about today is to better define what this maximum extent practicable means. And so the next few slides will go over what that acceptable range is. So, and now I'll give it to Scott.
Thank you, David. Good afternoon, everybody. Most of you probably are aware of the Massachusetts River and Stream Crossing Standards, but I'm just going to do a quick overview for those of you who may be less familiar with them. They were developed about 20 years ago to provide some standards for road stream crossings that would allow fish passage and the movement of wildlife. And so in that way, they actually are useful for addressing 2 of the 8 interests of the Wetlands Protection Act: fisheries and wildlife habitat protection. And the standards include having a span that's at least 20% wider than bankful width, so 1.2 times bankful width. We prefer open bottom structures that preserve the integrity of the stream channel that's there. There should be substrate, so that if it's a closed bottom structure, there should be it should be embedded so that there's substrate. That substrate should match what's in the stream itself. There should be bank edges on each side, and you should have a constructed channel that will concentrate water at low flow and allow water passage at higher flows, and therefore maintain comparable depths and velocities through a range of flows as the stream goes through the structure. And then there's an openness ratio, which is basically cross-sectional area when measured in feet divided by the length of the structure in feet, to try to provide enough openness so that wildlife are likely to use the structure. And so this was incorporated into the regulations about 10 years ago, and with the language that for replacement crossings, you need to meet these standards to the maximum extent practicable. And it's been a question ever since, so what does practicable mean? And it's become clear that one of the issues that has to be addressed when providing guidance on that is cost. And so when we think about what's practicable, it has to be some kind of a cost-benefit analysis in terms of the environmental benefits that you get relative to the financial costs. So one of the challenges with providing some guidance on that was trying to figure out what's a baseline for cost, so that you can say something to the extent of, up to 20% more than that cost would be practicable, or up to 50% more. And so when we thought about what's a suitable baseline for evaluating that cost-benefit ratio, we would consider 2 other interests protected by the Wetlands Protection Act: flood prevention and storm damage prevention. And so, next slide, please. So what we wanted to do is develop some minimum hydraulic design criteria that would protect against flooding and against storm damage, and use that as the baseline for what would be considered the maximum extent practicable, up to the point of actually fully complying with the stream crossing standards. And so it's essentially establishing a floor that you really don't want to go below. And so what was customary in a lot of cases is replacement in kind was the baseline. And many times those structures are already undersized, and it would be inappropriate So you'll see here that, for most municipalities, we're talking about needing to pass a 10-year storm or a 25-year storm. And for larger roads, it may be 25, 50, or 100-year storms. Next, please. So as David said, there's at least 25,000 road stream crossings in Massachusetts, probably many more. And bringing them up to standards is not going to be an easy thing, and it will be costly in aggregate, but it's also important as we consider climate change and the vulnerability of road stream crossings to the kind of severe storm events that we've been seeing more of late. But we recognize the need that the guidance has to be practical in order to be applied. Next. So that's why we decided that there had to be in the guidance document a cost-benefit analysis. And so, that would be essentially aimed at, what additional costs would be considered practicable. And that baseline, again, is the hydraulic design criteria. But how far above that you need to go would be based on the habitat quality of the stream that's being crossed and the connectivity restoration potential if you were to upgrade that crossing to meet the crossing standards. I'll cover both of those in just a minute, but it's also important to recognize that if a replacement project was deemed not to be practicable in terms of meeting crossing standards, that doesn't give them a free pass to do whatever they want. They still have to do whatever they could do within that cost constraint to maximize aquatic organism passage. So that means things like maximizing crossing width, using rock or log weirs or rock veins to backwater the outlet or reduce velocities, or to do stuff in the channel in the structure itself, like a roughened channel to reduce velocity and ensure adequate water depth. Next. To establish what qualifies, under habitat quality, we used 5 GIS data sets that were available statewide. The biomap aquatic cores, cold water fisheries resource, diagenous fish runs, areas of critical environmental concern, and wild and scenic rivers. We consider the highest quality stream segments will be those that meet 2 or more of these categories. High quality would be one of those categories, and everything else would be considered in a general quality category. We're assuming these are are presumptions, and therefore, if there's site-specific information that could be considered to change the standard for a particular stream reach, that could be considered on a case-by-case basis by the Conservation Commission or DEP. Next. To classify areas in terms or crossings in terms of connectivity restoration potential, we propose using the critical linkages project that we did here at UMass Amherst, where we evaluated the aquatic connectivity improvement that you get when you upgrade a crossing to be fully compliant with the crossing standards. And we have one version that looks at all of the structures statewide, and we decided that in that category of highest restoration potential, those that are in the top 5%, so in the upper 95 percentile, those are going to be in this highest category of highest restoration potential. In addition, we have a version of critical linkages that's specific to cold water stream segments. And for cold water stream connectivity, we're saying in the top 10% puts you in that highest category for restoration potential. And then as you look down the list, you can see the other categories: very high restoration potential, high potential, medium potential, and other. And you can see the percentile thresholds that are there that would qualify crossings into each of these categories. Next, please. And then this is an example of how we might then turn that into cost factors, where if you're in the category where you have the highest quality habitat and the highest restoration potential, you're going to have the highest additional costs before you consider that not feasible anymore or not practicable. And so, we have not yet finalized this chart, so this is just for example, but this is the kind of chart that you can expect to see in the guidance to indicate just how much above baseline costs you need to go in order to be considered no longer practicable. Next. Back to David.
Yeah, thanks, Scott. So, where is the proposed policy and guidance document at right now? It's under internal review. We're still discussing a few things like finalizing the cost ratio table. But we've gotten some internal feedback from the regions and incorporating that feedback into new drafts. And then following our internal review, we'll also loop back with an advisory group that we've established for additional input and review. Next slide, Gardner. So at the beginning, when I went over the agenda, I said there were two main parts to this presentation. One's the proposed policy and guidance, and then the other's the actual statewide hydraulic model. So now we're transitioning to the model component part of the presentation. And so the target audience or end user of the tool is DPWs and towns, although it will provide some value to consultants as well. But the towns that aren't doing any designs currently for replacing stream crossing standards or for replacing stream crossings, because they're replacing failing culverts in kind. So unfortunately, many DPWs in towns, they don't have an engineer on staff or a current on-call contract with a consultant. So they're unable to reasonably estimate adequate sizing of culverts and other crossings when a road fails from a large storm event, or if they want to plan for future resiliency. And so our statewide hydraulic model, as a preliminary design tool, will provide communities with that necessary preliminary design that would be integral to prioritizing capital and long-term planning. And so my next slide goes into this a bit further, but first I want to provide an overview of the phases that we've completed or secured funding for so far. So phase one, we conducted a feasibility study, and our deliverables for that were a USGS geo-narrative and then the draft MVP guidance document that Scott just went over. For phase two, we developed a pilot basin, and this was in stream stats, and that included the beginning of the model development and automation of all the stream crossings within that Squanicook Basin. Phase 2A was a collection of data for calibration purposes. So this phase was integral to ground truthing our methodology, which creates elevation data based on bankfull equations. And then we compared that to a more traditional bathymetric survey methodology. And then phase 3 and 3A, we've gotten funding for this year, and that will be put towards scaling of the model watershed by watershed. So next slide. So my goal of this slide is to show you how the tool fits into the design process to encourage adequately sized crossings that move away from replacement in kind. So the blue loop on the left shows what we want to eliminate. It's stream crossing replacements occurring in kind. And then the black loop on the right shows how the preliminary tool is used to create resilient stream crossings. So our goal is to be able to provide project prioritization and preliminary sizing for budget planning and grant applications. And so as you can see, the left loop has no tool and creates this never-ending loop of undersized, non-compliant crossings. The black loop on the right shows the statewide model will break this loop. And then the end goal is to facilitate the replacement of undersized culverts with more resilient crossings. And the statewide hydraulic model is a key part in this. So this example really just kind of shows one application of the model, where it's, following a road failure, but there is the more proactive application of the tool, the one that provides the preliminary designs for capital prioritization, grant applications, so on and so forth. So with that, I'm going to hand it to Gardner.
Thanks, David and Scott. Can everyone hear me all right? Just checking. Okay, so David talked about how we've started to scale this. So I'm going to kind of focus on the pilot watershed. I might talk a little bit about our phase 2A, which was statewide. So initially we looked at the Squanicook River Basin and we selected 16 sites where we went out and we field surveyed those for the comparison. And then we kind of varied those. Typically, a lot of stream crossings are going to be on small watersheds. So we picked small watersheds. We picked varying slopes within the Squanicook, which is in north central Mass. We're kind of up in this area here in the pilot watershed. And then for phase 2A, we moved across the state. And again, we tried to vary the drainage areas. We went a little higher, but generally smaller drainage areas, less than 5 square miles. And then we varied again the basin slopes. And also we varied the NAC stream crossing assessment. That's supposed to say not possibility score, corrected on me, but passability score is what it's supposed to say there. So next I'm going to kind of talk about so we're focused on, we collected this field survey data, and we want to compare those hydraulic models to what we'd get with automated, we'll call them GIS-based hydraulic models. So everything's going to be automated in those, and we want to compare those two to make sure we're doing a satisfactory job with GIS-based before we scale it up to these larger watershed-based things that David talked about here. So the first thing we're going to talk about here is it kind of shows this is what we'd see out in the field if we were looking like upstream, the upstream face of the structure, downstream face of the structure, and looking downstream. And we're going to get into more details, but we're going to basically take all that information and we're going to end up with our HEC-RAS models. We evaluated several different models and we ended up choosing HEC-RAS. And you can see here, this is the DEM from LIDAR for that particular location. And so what we're doing is we're defining that watershed, the stream and the watershed at that stream crossing. So we have, 1 meter DEMs, and we're deriving the stream network and the upstream watershed for those particular locations. We're taking that information for the DEM derived watershed drainage area to then use that with the Massachusetts peak flow equations by Zariello to compute the different, the 10%, the 10, the 4, the 2, the 1% AP flood flows for that particular location. So what the process of the GIS-based scripts do is that we have that hydrography derived by the LIDAR data. And so it's going to go in and the functional, so it's going down that stream reach. It's finding inflection points. So here it finds the upstream face, finds an inflection point, hence the road deck, which isn't necessary, but we want to know whether water is going to go over the road deck. And then it finds an inflection point here on the downstream face, and then the approach cross section and exit cross sections are essentially two bankful widths upstream or downstream from the upstream face, or downstream, or upstream and downstream face respectively. And then as we know, LIDAR doesn't necessarily capture the channel geometry. It's going to see that water surface elevation. So what we determined is we needed to burn in a channel, for those cross sections. So in this particular case, we decided to go with the bankful channel geometry equations, where we have bankful width and depth, and that is burned in here. So you can sort of see, this is what you'd see from the LIDAR data. And we're taking that and we're burning in a trapezoid based channel based on the bankful depth and width. And, right now we're using a trapezoid. We've looked at a couple publications. We might go to a parabola, but right now we're using a trapezoid. It's very similar, but just if we were improving it, we might go in that direction. So next, what it's doing is it takes those cross sections. We have Python scripts that are run, and it's going to take all those cross sections in the burned in channel, and it's creating the HEC-RAS geometry file. Then additionally, it's creating automatically the project files, the plan files, and the flow files. And again, the flow files are the flows from Zariello's peak flow equations for Massachusetts, and it's creating those in the format, all the input files needed for HEC-RAS. And then HEC-RAS automatically runs, and we're going to get our basically our preliminary culvert designs from that. So in this case, now I'm going to kind of shift backwards a little bit. So when we're doing those comparisons, what we did is we took a look at what the existing conditions are out there. So based on the field survey, we just wanted to say is what kind of culverts out there, and what kind of, how does it work with the different AEP flood flows that we have. So in this particular example, this was in the Squanicook, and we have a pipe culvert that's 2.5 foot diameter pipe. And we can see that basically, and this is true of a lot of the things, the 10-year or the 10% AEP flood flow does not go over the road deck, but obviously everything's filled and there's backwater. And then we can see that once we move beyond that 10% AEP flood flow to the 4, the 2, the 1%, and the 0.2% AEP flood flows, the water's going over the road here. And we can see here that based on the stream crossing standards, or the span divided by the bankful width, which Scott talked about wanting to be 1.2 times, we're only at 0.2. The openness ratio, we wanted to be at 0.62, we're only at 0.08. So that's just kind of showing what we saw that was out there. So next we're going to get into a little more. So now this is with preliminary culvert design based on HEC-RAS. And what we're doing is we're trying to meet the stream crossing. We're designing for that minimum hydraulic design that Scott was showing on that chart with the arrow across it. So we're developing minimum culvert designs for the 10 and the 4% AP flood flows. And then we're also making a design currently for the that meets the stream crossing standards. So in this particular case, this is an example of meeting the stream crossing standards. I believe this is the same location I just showed on that slide, but we can see here for the stream crossing standards, we're passing all of the flood flows from the 10% AP all the way up to the 0.2% AP flood flows, and we've met the stream crossing standards in this particular case. So when we're doing all this, and these are only results for the Squanicook right now, but the things we asked ourselves are, do we get about using the GIS or the LiDAR derived DEMs and the field surveyed elevations? Do we get about the same elevations? So we're just comparing here the elevations like of the approach cross section thalewag, the upstream face invert of the culvert, and the downstream face. And we can see here that we're about a foot higher with the GIS, but basically we're still, this is 0 here. This is doing a pretty good job. We're within about a foot of what it actually is out in the field if we field surveyed it based on the LiDAR derived DEMs. So we thought we're doing a pretty good job here. Next, we wanted to see, like, when we create these hydraulic models, do we end up with water surface elevations? How do they compare between the field-based model and the GIS-based model? So we did this comparison. Do we end up with water surface elevations at these different flood flows that are about the same between the two different modeling techniques? And we can see here again that we're a little less than a foot difference in the water surface elevation between the two different models. So again, we think we're doing a fairly good job. So then next, I think we think of, do we end up with the same preliminary culvert design based on whether it's the field-based model or the GIS-based model? And essentially here we can see here that for the box culverts, so we did 3 different designs too. So we have the 10% and the 4% AAP flood flow, and then to meet the stream crossing standards, and we're providing a box culvert design, a 3-sided box culvert design, a 3-sided conspan arch, and then a pipe design. So in this particular case, we can see the median differences between, for the box, the span, the height, and the cross is 0. And for the conspan arch, again, there's the median difference is 0 for these 60, whatever, how many of the sites we could come up with solutions for. The pipe culvert, there was a little difference, but it's relatively minor for the comparison of those couple models. So next I want to talk about, and I'm going to try to do a live demo. I think it'll work here. But we've taken that information, the preliminary designs, we've taken the aquatic habitat quality score that Scott talked about, the stream conductivity restoration potential score for that location, and we brought that in. How do we serve this to the public or a community? And so we decided that we could do that through stream stats that many of you may be familiar with. So we've developed it's a development stream stat site, but where the user will be able to go into Massachusetts, click on a stream crossing, and get a report with all this information, general information about the site, as well as the preliminary culvert designs. Okay, so let's see how this works. So again, like I said, we're going to get site information. We're going to get, we've linked it to getting information from the North Atlantic Aquatic Conductivity Collaborative. That's the stream crossing assessments. So the user can see what was the passability score. We got the information on the aquatic habitat, stream conductivity restoration potential, and then we got the MassDEP highway functional classification. Scott showed that chart, and the associated hydraulic design flows. We have the Massachusetts peak flow equations, bankfill channel geometry equations, those results there. And then we have the different preliminary culvert dimensions and its relation to the mass stream crossing standards. Oh, no, it didn't. I guess it's not going to happen here. It should work. Let's try this here. I'm just going to make it work. So here in this particular case, if we were interested in the Squanicook, so this is the development site. It's not out to the public yet, but this is kind of what it's generally going to look at. But if I typed in, I know we did some work with the Squanicook involves Ashby, Mass. If I knew I wanted to go to Ashby, Mass or Squanicook, I can just type that in. We go here. It's just like the regular stream stats. We're going to zoom out a little bit to see we're in the thing. We're going to pick Massachusetts because we're in Massachusetts. And we see the stream crossings pop up here as these red dots. Like here, I can take this and I just click on this. And it comes back with a little pop-up, which has the survey ID from the NAC. This is the habitat quality score Scott talked about, high quality, restoration conductivity potential, high restoration potential. Currently we have this in that's going to, until we get it finalized, that's going to come out. And then we have the hydraulic design flood for this particular, what MassDEP says it is. So we're going to hit here, we're going to build report. We can see here that it drew the watershed here. There we go. It drew our watershed boundaries for this particular location. We're going to hit build report. So everything's pre-solved. We didn't have a way, maybe in the future it'll be something that it can run dynamically. Someone might be able to change parameters if they want to and rerun it. But right now we're not at that level. We're just trying to get this to work. So we have the pre-solved solutions, and we can see here, it comes back, looks just like a regular stream stats report. We can see the basin boundary here. We got our lat long for where we picked. Here we got the NAC ID, the NAC stream crossing code, and you just hover over these eyes and it tells you what these are, where we are. I'm on New Ipswich Road. The stream name is Trap Falls, and it's in Ashby. I keep moving down through the report. I have the basin characteristics that went into solving the peak flow equations and the bank fold channel geometry equations. And we have all the links there to the reports. Then we come down here, we have the habitat, the individual parameters of the habitat quality score. Again, there's the eyes, you can read about them. And then it gives based on what Scott talked about, if you have one of these fits, then you're a high quality. If two fit, then we'd be in the highest quality. We have the restoration conductivity potential score here. And then we have links to all of this here. We have the road crossing characteristics, again, from MassDEP, what the road classification is, hydraulic design, what the flood flows are based on the mass peak flow equations, bank fold channel geometry. And now we come down to what you're probably interested in is here we can select, we see there's the box, we can select this report, we can select the arch and the pipe, and we can look at each of these. We're just going to work on the box, three-sided box culvert, and we can see here what's the span for the 10-year flood, the 25-year flood, or 4% AP. What meets the stream crossing standards? Again, what's the box culvert height for that? What's the box culvert length? The culvert area in square feet. What's the material of the culvert? We're using concrete for everything, but again, besides the pipe, the arch and box are three-sided. So, but the material here is we're using pipe, gives you the upstream channel invert, the downstream channel invert, what the road deck elevation was that was from LIDAR previous to that. And then it also tells you what that box, the maximum flow it can handle with at least some freeboard, right? So in this case, sometimes it'll be even for the design for the 10-year might be able to handle the 25-year, or that the 25-year design might be able to handle the 50-year flood. So that would be in there. And it shows you here for the stream crossing standards that it would pass with no backwater up to the 0.2% AP flood flow. And then here we're just looking at what stream crossing standards does it meet? So okay, here in this particular case, it's a three-sided box, so that meets the standard. We want that. There's no embedment because it's a natural bottom. So for the pipe here, it would tell you that it was embedded. It's a natural substrate, and then here it tells you what the span ratio was. In this particular case, it ended up being 1. I'll have to check that. It seems like it should have been 1.2, and then it gives you the openness ratio. And if it doesn't meet some of that, then it color codes it in orange, so that stands out to you, right? So then there's just some general disclaimer things which we're going to want to have, because ultimately someone's going to want to hire an engineer to come up with that final design. This is just a preliminary in the ballpark. This is the kind of sizes that you would be looking at. And now I think one of the really key things I think of this product here is that down here we can download, you can download the report, but if I come all the way down here, you can download those HEC-RAS files. So if you were a user and this gave you a preliminary design and you wanted to go in the field and change the Manning's N value, you have those HEC-RAS files. You can edit those and rerun HEC-RAS outside of StreamStats right now. but the user has the ability to download these files that were used to create these preliminary culvert designs. So I think that that is everything that I had on my list of things. I'm just going to move through these because this was just in case the web application did not work. And I'm going to turn it back over to Scott, and then, to David, and then we're going to have questions.
Yeah, thanks, Gardner. So obviously we have a lot of work going on. One of my last slides showed the phases, and I think we have 3 current phases. But that said, our goal is to overwhelm USGS with as much work as possible. So we are thinking about future phases here. The stream crossing planning tool incorporating the coastal areas. We have some momentum on this. We are positioning for a wetland program development grant application in the next few weeks. That would include coastal crossing design standards, as well as some tidal hydraulic geometries. And so we'll kind of finalize those details here in the next few weeks. And if we get the funding, then we would expect to have that here in the next several years. Stream crossing planning tool incorporating the future flows. We are committed to that, but we are a couple years away from receiving the future flows. But we'll incorporate that when we get them. And then another idea that we've just been tossing around is the inland flood extent and depths for the future flows. And so this would supplement the current FEMA maps. And so that would be a little bit different. It would consider more of the existing conditions rather than proposed conditions. And so we want to discuss that more. But anyway, that's could be a potential phase at some point in the future. So with that, though, we can take questions.
Okay, thank you so much. I'm not a scientist in any way, shape, or form, but that was fascinating. So people can unmute themselves or put their questions in the chat. There is one question in the chat, and that is, does the tool show you what the existing culvert size and type is?
So I'll take that one. Right now, it does not, but we have to, so there would have had to have been an assessment. We have talked about, again, mining where there is an assessment. So if there was a NAC assessment there, we could provide that, the current structure that was there, or the information from that NAC stream crossing assessment. We could apply it, and then we could just say, if it wasn't available, it's not available currently. So, but that the only issue there is then we have to, which we can do again, is like maybe yearly we'd have to go and remine what is there. And Scott might have some ideas on this or another function that provides that to people too. So I mean, anyone could go to the NAC and look to see if those existed already too. But anyways, I'll stop there.
Yeah, I guess I'll just add that, at this point, we're still just sort of working on pilots and starting to build it out. But at some point, it may be possible to link the NAC database with the USGS database so that it could be updated sort of on a daily basis automatically. But we have not discussed that nor explored it with the technical people to see what that would involve. But we have linked our database with other state databases and the DOT database so that they could get regular updates as new assessments are done.
Okay, great. I'm keeping an eye on the participants that might be raising their hands. I don't see anyone raising their hand right now, but I do see just a new question now from Kimberly McPhee. Kimberly, would you like to unmute yourself and ask that question?
Oh, sure. I don't know where my camera is focused. Let me see.
That's better.
Is that better?
Yes.
So I have this I have as I said, vague and unpleasant memory that after Tropical Storm Irene, it was really hard for our communities to get reimbursement from FEMA for upsizing their culverts. And I'm wondering if now that, we have the stream crossing standards, and when this guidance is kind of live, will that help with communities wanting to do, either pre-disaster or post-disaster mitigation work? And I mean, maybe the question is not timely in terms of the current audience that we have, but it occurred to me, so I thought I would ask it.
I think we're hoping that it will help. My understanding is that FEMA was skeptical that our crossing standards were really being required of municipalities and other applicants, and that it was really uneven in terms of how it was being applied. And therefore they weren't really requirements. They were just sort of suggestions. And part of what we diagnose as maybe one of the reasons why it wasn't being more universally applied is because of cost issues. And that once we can clarify what the cost benefit ratios need to be to define something as impracticable, it would be easier for conservation commissions and DEP to consistently apply that policy and that guidance, and make it easier for us to demonstrate to FEMA that this is a legitimate requirement.
Great. Thank you, Scott.
Yeah, I think that's right, that post-disaster, especially if you're looking at public assistance money, the money that they give is based on state and federal requirements. So if it's not a requirement, then it's sort of considered by FEMA to be just a lovely wish that the community would have, but not anything that they're going to necessarily fund. Matt Schultz, you've got your hand up. Do you want to add to that?
No, I just had a different question. I guess sounded like you guys had built this out in certain pilot areas, and what's the plan to building out, or is there a plan to build this out throughout the entire state, and kind of what the timeline is on that, if I understood that correctly? And then maybe a couple other follow-up questions in terms of which HEC-RAS models that would be downloaded, you could download it. Would that be for just a specific crossing, or if there's multiple crossings, would the model extend? I'm just trying to figure out what the extent of that HEC-RAS model would be. But very cool to have that data available to us, so I appreciate that.
So
go ahead, David, and then I'll answer the second half.
Gotcha. Okay, so yeah, the scaling of it statewide really depends on funding. And so our what we're calling our phase 3 and 3A, which is really our 4th and 5th phase, that will include the build out for the Deerfield, the Housatonic, the Hudson, and the Westfield watersheds. I think that answers that question. Gardner, do you want to touch on the second one?
Yeah, so for the second one with the HEC-RAS files being downloadable, so you'll be able to get all the input files and the output files. So every HEC-RAS file that's associated with that structure, you can download from StreamStats. But additionally, for us to put it on StreamStats, all of these models will be published in ScienceBase as a data release, right? So in that particular case, if you said I'm interested in all the stream crossings, let's see, that if we did a watershed, and let's just say the town of Worthington was in that whole watershed, you could go into the USGS science-based data release and download all of those instead of clicking on every single one.
Right.
So that's it. So there's really almost like 2 locations where that data will be.
Right.
So that'll, I think, hopefully help people. We're trying to figure out how we're gonna, because it's a big leap here. We're going from 30 or 46 total sites in the state to, we'll say just the Westfield and up of Housatonic, we're looking at like 1,200.
Right.
So how we're going to serve those easily, but I think that the data release is really going to be if people want like a whole town or a river reach, like like I want everything on the South River. Well, in Conway, well then you could go in and grab those from the data release.
Cool. Thank you.
Dave Woodbury has his hand up.
Hey, good afternoon, everyone. I'm sorry I was late to the webinar, but I really appreciated what you were sharing. I just wanted to briefly just follow up on Kim's comment regarding Irene specifically. And I'm glad that Scott mentioned the cost benefit sort of analysis, because I would envision that's probably what was some of the concern as it related to upsizing. So in the public assistance FEMA world, they do have hazard mitigation. It's called 406 mitigation, but it does require a benefit cost analysis to be run. And so we don't see a whole lot of it. Oh, I should stop by saying I'm Dave from MEMA in the hazard mitigation unit. It seems to us, based on experience, that FEMA Region 1 really doesn't take advantage of that 406 mitigation. But we certainly are, very much involved in culvert upgrade projects in our what's called 404 mitigation for the actual hazard mitigation assistance. And we definitely try to promote as best as we can and illustrate to our FEMA Region 1 hazard mitigation assistance counterparts the importance, of meeting those stream crossing standards to the most practical extent possible. And it even shows up in our rankings when we convene, state and federal partners to be on our review committee once we have an open grant application period. I think that, that factors into the rankings, having that beneficial, meeting the stream crossing standards. So I just wanted to add to that. And FEMA Region 1 is also very risk averse, so they most likely would feel more comfortable just repairing damage to what they find rather than being more proactive, unfortunately.